Hello, my friend.
To create this video I needed to put in more effort than for my other previous videos. So, unfortunately, I have not published another new video on my channel for a long time. I hoped for the understanding and tolerance of my viewers because it took a lot of work. In addition, it took a lot of time to comprehend and develop the theoretical part. Since I could not find ready-made information about this technique in full, although there were references to it with a general description. I had to develop the methodology myself. I hope I didn't make a mistake.
I have acquired several microcator of a rather unique design. This microcator with a side-acting probe is functionally similar to a lever-type side gauge. Its probe can be switched to operate either from bottom to top or from top to bottom. However, its sensitivity is 10 times higher. Namely not 1/100th, but 1/1000th of a millimeter. The design of this device inspired me to create a special stand for it. When mounted on such a stand, the side microcator becomes a very useful, convenient, and multifunctional measuring device. But its main and unique advantage is the ability to obtain accurate data about the geometry of the measured surfaces, surface plate, and straight edge, without having a basic high-quality straight surface on the straight edge and surface plate used during these measurements. In other words, regardless of the geometric imperfections of your straight edge and surface plate, after the measurements, you obtain precise information about their geometry and the degree of deviation from ideal straightness. Your capabilities are significantly expanded. The stand can be transformed for various types of measurements, including measuring right angles. The most complex and crucial operation in the stand's fabrication process was creating a sufficiently precise surface for the supporting feet. Initially, they were ground on a surface grinder. The legs themselves are made of hardened steel from a metal cutting mill. I attached them with epoxy glue, but this is not the best solution. In the future, I will solder them with low-temperature, soft solder based on tin to ensure they are securely attached and do not lose their hardness. The pre-ground supporting soles now need to be lapped to increase their accuracy. I will perform lapping on this steel plate. It is almost flat, but this central part is 3 microns higher than these two opposite corners. I will take this surface feature into account. The detail is prepared. First, I apply a coarser abrasive powder. This is a soft abrasive, and I'm not exactly sure of its brand. Based on my previous use, I know it will quickly break down during lapping and will be easily removed from the surfaces afterward. I add a bit of kerosene, spread the abrasive powder on the surface, and conduct the initial rough lapping. Of course, this will take about half an hour, but for you, it's just a minute of this monotonous work. Now I apply very fine abrasive powder. This is also a soft type of abrasive. As you can see, I use a higher part of the plane, gradually erasing it and making the lapping plate flatter. In the lapping technology, I need more practice to understand the nuances of this process more thoroughly. But in this case, I know I will get a flat enough surface for the stand to work properly. The soles will be oriented to a common plane, with only a very slight convexity in the center of their geometry. It is possible to see the result in monochrome light. The center is convex by a little more than a micron. Thus, everything is done, and the stand has turned out as intended.
Працює зверху вниз.
It allows measurements with the vector either upward or downward, working from top to bottom or bottom to top.
Працює знизу вверх.
For example, I will measure the gap between a very flat surface plate and a perfectly straight edge. I set the straight edge on two identical gauge blocks, each with a height of 30 mm. Don't worry about me touching these precise objects with warm fingers. During such a short contact, I will only slightly heat them, and their dimensions will change so insignificantly that for this measurement, the deviations are negligible. At the same time, I try to touch the surface plate, gauge blocks, and especially the straight edge as little as possible, since the straight edge will not only increase in size due to heating but also bend for a while. However, the deformation of the straight edge from brief hand heating will quickly pass as the heat spreads through the body of the straight edge. In about 5 minutes, its shape will almost return to normal because steel has fairly high thermal conductivity. Now I intend to measure the gap between the surface of the processed surface plate, which I carefully flattened, and one of the edges of the straight edge, which I also additionally aligned. During the additional alignment, I lapped this edge of the straight edge to the flat surface, and this lapping process was technologically simplified, so the edge of the straight edge turned out straight in the center but rounded at the edges. At that stage, it was acceptable for me. Such a result is better than its initial more curved state. If desired, the lapping can be done in a more technologically complex way to achieve a completely flat surface. You can see that there is high repeatability in the measurements. This is approximately how the microcator probe ball interacts with the convex surface of this edge of my straight edge. This is how I conduct measurements at 5 arbitrarily chosen control points. Now, let me demonstrate how measurements are conducted under conditions close to ideal, when the surface plate is flat, and the straight edge is straight. In each measurement point, the arrow occupies one position. This is surprising, but in an ordinary workshop, in conditions that were not laboratory at all, without the use of expensive high-precision instruments, it was possible to achieve an accuracy that can be called almost sub-micron. Once again I demonstrate the repeatability of the measurement, which is ensured by the special sharpening of the support pads that displace dust from the surface of the surface plate. But I'm making this video for a different purpose. This device allows precise determination of the state of the surface plate and straight edge even when the surface plate is not perfectly flat and the straight edge is not perfectly straight. It just requires conducting 2 measurements instead of 1, and then performing simple mathematical calculations based on the results of these 2 measurements. This way, you obtain accurate data on the deviation of the measured surface plate from straightness along the measurement line. At the same time, during the same measurement, deviations from straightness are determined not only for the surface plate but also for the straight edge used in the measurement. This fundamentally changes the situation. Your measurements become undoubtedly reliable since they no longer depend on the accuracy class of the straight edge or the accuracy class of the surface plate available to you. Now watch how such measurement is performed. I have a plate whose surface is not perfectly flat. It was damaged by corrosion, and I cleaned it with sandpaper. Now I will smooth the surface using a steel parallelepiped. Steel slides well on cast iron, it will level microscopic scratches from sandpaper, providing good repeatability of measurements. The surface is carefully cleaned, taking much longer than I demonstrate in the video. I place a straight edge in such a way as to use its not completely straight edge, corresponding to a low standard of straight edge quality. The first measurement will be the gap between this non-straight edge of the straight edge and the surface plate at 5 control points. For a better understanding, I created a model with deviations from straightness increased 1,000 times but corresponding to real deviations of my surface plate along the measurement line on a 1000:1 scale, and the straight edges are similar. Now, I will show on the diagram how this double-averaged measurement of surface linearity is performed. The first measurement and the first set of data are obtained by measuring the gap between the surface plate and one of the edges of the straight edge. Here is the real-world action. I arbitrarily selected 5 designated control points, and specific linear data of the first set of measurements, let's call them red, appeared. The microcator sensor works from top to bottom. Now, I reconfigure the microcator to the next operating mode, specifically in the opposite direction, from bottom to top, and to the next height position of the probe. I am preparing to conduct the second set of measurements. For the second round of measurements, it is necessary to flip the straight edge by 180 degrees, but the straight edge should not move right or left. Any movement of more than a few millimeters is considered undesirable, as a couple of millimeters of such displacement will not distort the measurement results. The next series of measurements is conducted at the same points, resulting in a new set of measurement data, let's call them green. In order to tell as accurately as possible about the technology of such measurement, I prepared an animation. We have surface plate and straight edge, the working surface of which is not ideal. Since this is an animation, all the irregularities are exaggerated to be obvious, but I made them in this animation corresponding to the real ones on my straight edge and surface plate, only I increased them in the vertical direction 1,000 times. We create a cross-section of the surface plate along the measurement line. We make deviations of the surface plate surface from ideal straightness clearly visible by superimposing an image of a straight line emphasizing the deviations. Now a simplified image of our device appears. We choose a convenient point to set the device to 0 for this measurement. This is the place where the gap between the surface plate and the bottom edge of the straight edge is maximum. As the gap decreases, the readings on the instrument scale will increase. We get the first data set. Graph in red colors. The control points are bright red. For the second round of measurements, we turn the ruler over. Then we switch the microcator to the reverse operating mode. Now the microcator works in reverse, from bottom to top. The larger the gap, the higher the reading on the instrument scale. We now adjust the 0 on the device scale to the smallest gap size between the surface plate and the upper edge of the straight edge. We carry out the second round of measurements, we get the second set of data. In our animation this is a green graph. The red and green graph, as we now see, are connected by a line that is identical to the surface plate surface. This makes it possible to obtain information about the deviation of the surface plate surface from the ideal straight shape at each measurement point, through mathematical calculation. Here is the formula for this calculation and the logic of its implementation, expressed graphically. This is the second version of the graphical representation of the logic of this calculation. Let's imagine that our surface plate is completely flat. If the surface plate surface were absolutely straight, as it is now in the animation, then the data from both rounds of measurement would be identical, and would reflect only the degree of unevenness of the straight edge at each of the measurement points. Look at the data red and green graphics. We return to the animation to the original, that is, uneven state of the surface plate. You need to understand that some inaccuracy in the position of the straight edge relative to the surface plate surface will not affect the measurement result, or rather, it will affect it negligibly. The data themselves will change, but the final measurement result, if it changes, will only be by a fraction of 1%. The blue line in this case graphically shows the absence of changes in the final calculation results, although the numbers in them will change. But the topography of the measurement line will not be distorted. This means that the information about the rises and depressions on the surface of the plate and the linear dimensions of these irregularities will still remain correct. A small shift to the right or left will not significantly affect the results, but such a large shift should not be allowed. The height position of the straight edge relative to the surface plate will also not affect the measurement result. Using the data obtained, using another formula, you can similarly calculate the shape of the straight edge. Now I will carry out these measurements on a real surface plate and straight edge, and you can watch how this happens in real life. By the way, deviations from straightness in this case will correspond to those that were applied on the animation model in a proportionally increased size. Results of the red measurement. The results are entered into the Excel table. Accordingly, a graph has been created in the table for clarity. This is the red line on the graph. Green set of measurements results. Green results are also included in the table. There is a green line on the graph. Processed measurement results according to the calculation formula, column X in the table. This is the purple line on the graph. This purple line reflects the surface topography of the surface plate. Since the other side of my straight edge is straight, I have the opportunity to check if my calculations add up with the measurement of the surface plate relative to this second, straight edge of my straight edge. I'm taking another round of measurements. I'll call it yellow. We will see how accurate the measurements and calculations were made using the reversible microcator and the double reversal measurement technique. We receive this measurement data, now I process it and get the surface topography of the surface plate. I'm comparing the results. On the graph, the purple line is supplemented by a new, yellow line, the result of the latest measurements. There is some discrepancy in the final results, but only within 1 micron along the entire measurement line, which is 500 millimeters. This discrepancy reflects the degree of accuracy of the measurements taken. This error is not large, and is caused by the low quality of the surface plate surface, and the lack of ideal laboratory conditions when carrying out measurements. I developed this stand independently, and I also devised the calculation methodology independently. I do not exclude the possibility that I may have made some mistake or taken a less rational path, but I hope that this is not the case, as in this practical measurement, everything seems to align. If anyone has relevant information, please write in the comments or email. My main goal in my current activity is the development of my YouTube channel. I want and can provide my viewers with a lot of interesting and useful content. If any part of my audience finds my work helpful, and at the same time is able and willing to support me through Patreon, I will achieve success in this project more quickly. Over time, direct income from YouTube will allow me to successfully grow my channel, but support is crucial for me right now. I am grateful to all my viewers, but doubly grateful to those who support my work. I will show another application of this device. With its help, I can obtain information about the geometric shape and dimensions of a steel cylinder with sufficient accuracy, down to a micron. This becomes possible thanks to the very precise surface of this surface plate and the device's ability to measure both the gap from the surface plate to the bottom edge of the cylinder and the distance from the surface plate to the top edge of the cylinder. It is crucial that the cylinder itself remain stationary from the first to the second series of measurements, allowing us to fully reflect its geometry, including the diameter at each point and its straightness. I managed to find an almost straight section on the surface of this cylinder, and install it exactly parallel to the surface plate. Therefore, the readings of the device are the same everywhere. Now I find out its dimensions in this section with high accuracy. The result of this measurement. By conducting these measurements on the cylinder and subsequently rotating it 90 degrees or, let's say, 45 degrees 3 times consecutively, we obtain very accurate data about its geometric shape and dimensions. The device reflects small changes in size, and to better understand the overall size of the part, we can use gauge blocks to correlate the device's readings with the surface plate or simply measure the part additionally with an appropriate tool. The device copes well with right-angle comparison. In 15 minutes I managed to make such a miniature. I have about 10 of these side microcators in stock. If there are 10 people who want to buy such a measuring kit from me, then I will make 10 such kits and send them to customers. Write to anyone interested. I managed to acquire this fascinating device, largely thanks to the support of my patrons through Patreon, and I want to express my gratitude to them. This device is called an optical ruler, model OL800. By using it, I can detect surface elevations or depressions down to half a micron or more along an 800 mm measuring line. It's important to note that this is a direct measurement, unlike an autocollimator where measurements are sequential, and each subsequent measurement is tied to the previous one. In this case, when we talk about half a micron, it is genuinely half a micron at that specific point relative to the extreme points along the measuring line. I'm not aware of a similar device being produced in Western countries, and if it is or was, I would appreciate it if someone could share the information. Please feel free to leave comments or reach out via email. One of the upcoming videos will be dedicated to exploring and showcasing this device.
10, 11, 12, 13, 14. Thank you for your attention. Goodbye.